Hi everyone. Welcome to, this is actually lecture 25, not lecture 26. Seem to be having trouble with my lecture numbers in the last two lectures. Anyway, this is lecture 25. We're going to talk about the Tds relations, entropy change for an incompressible substance and entropy change for an ideal gas. And I'm going to try a little something different with the lecture today. Rather than going through lecture notes like normal, I'm going to actually go through my book style notes and just highlight some things there. Everything I want to say in the lecture is actually in my book style notes, so I'm going to go through that instead and just highlight some things as we go through that. Okay, so these lecture style notes that you see up here, these are actually pulled straight from my book style notes. So let me just scroll all the way down to get to the book style notes. Okay, the book style notes are at the very end of the set of lecture notes that are posted on Blackboard. So these Tds relations, let me just kind of give you some background on how we're going to, or why we use these. They relate properties to one another, just like the ideal gas law relates pressure, specific volume, temperature for an ideal gas. The Tds relations just give us a way to connect up various properties, namely entropy, and specific entropy, specific internal energy, pressure, specific volume, and specific enthalpy. So it's just what we call a constitutive law. It's a way to connect property relations. And we'll start with the general Tds relations. These will be true for all substances. And then we'll make them specific for an incompressible substance in an ideal gas. And again, the reason we're doing this is it gives us a more convenient way to find entropy than having to look it up in a table. So we can actually use a model, the incompressible model or the ideal gas model, to find entropy values. So, okay, so here we are in my book style notes, and the Tds relations just come from a combination of the first and second laws, as I mentioned here. We have we start with the first law written on this, the part that I'm highlighting right there. It's just the change in total energy equals the heat into the system plus the work done on the system. Right now it's written on a per mass basis and as well as a differential basis. So instead of a delta E, we have a dE, and instead of just having a Q, we have a delta Q. The curly Q delta here for the heat and the work just again signifies that those are path dependent quantities, whereas the regular D just has to do with that the total energy being a property. So just some notational things there. But anyway, that's the first law. And notice that I used with the subscript on the work, I have a plus, work done on the system. It's just a different way of writing the first law. Specifically, we're going to consider what are called pure compressible simple substances. These are ones where we don't have to worry about kinetic or potential energies, and the only work that we'll have to factor in is PDV work. And I should say right here that PDV work is considered internally reversible work as long as it's done quasi-statically. So that's just something to keep in mind. We'll come back to that a little bit later. Okay, so if we incorporate those things like the no kinetic or potential energy, then the total energy just becomes internal energy. So the dE becomes du, and then the work becomes minus PDV. Because just as a reminder, that I'm using the work done on the system, but you can always do the work done by the system. So if I wrote the first law as du equals, let me rewrite this. du is equal del Q into minus del W by. Remember that del W by is just going to be PDV work. So that's why we have the minus PDV. All right, and then what we're going to do is we're going to substitute in specifically for the delta Q here, making use of our definition of the entropy. Recall that the entropy we had written look like this. This is the entropy as an extensive property was just the integral of delta Q divided by the absolute temperature for an internally reversible process, if you recall that, and this is over the boundary. If we take the differential of that, then that just becomes a ds on the left-hand side. So what we're going to do is take a differential and do it on a specific or per unit mass basis. And then the right-hand side, and let me multiply through by the temperature, so then that becomes Tds is equal delta Q into. And so then we'll substitute this into the heat term, so that's where we get the Tds. And then the boxed-in relation here is just a rearrangement of that equation. So now we have a way to relate the temperature, the specific entropy, the specific internal energy, pressure, and specific volume. So again, it's just a way to connect up properties to one another, and we found it by combining the first and second laws. And then we can also rewrite it in terms of the specific enthalpy by just taking the definition of the enthalpy, H equals U plus PV, and if we take the derivative of that whole equation, then we'll end up with the equation I'm underlining up above. And then we can take that and do some rearranging and substitute it in, and then we get the second boxed-in equation. It's just the same relationship between variables from the first and second laws, but now we've just rewritten it in terms of specific enthalpy. So those two boxed-in equations are going to be useful for us because we can now relate various properties to one another, and specifically having entropy in there. And I just want to also give you just a little motivation for why we care so much about entropy. It's going to come down ultimately to we're going to use these TDS relations and the second law to try to find the most efficient ways to operate various properties. So again, we use the second law to determine whether or not a process can even occur. So we have to make sure that we're not producing negative entropy production. Remember the sigma in the entropy equation. Remember that entropy equation? I'll just jot it down up here. So entropy equation. This was from the last lecture. Looked like delta S is equal to the integral delta Q into divided by T plus the entropy production. So in order for a process to occur, we need to make sure that the entropy production is always positive or equal to zero. And positive if it's internally irreversible, and it's equal to zero if it's internally reversible. It can never be negative, right? And this comes from the second law. So what we want to do is see under what conditions we can produce sigma equal to zero, internally reversible processes. That would be like the ideal case. Cases where that sigma is zero is ideal. And so ultimately what we're going to end up doing is trying to we're going to use those processes, those that are internally reversible, as kind of our ideal situation to compare against. And it'll give us a way to determine the maximum efficiency for various components and things like that. So ultimately, we'll end up using entropy to determine whether or not a process can occur, and also to determine what's the optimal, the best way that process can operate. Okay, so that's where we're headed to eventually. All right, let's get back to our TDS equations. The first note here just says, even though we've used the TDS equations, they were derived for an internally reversible process. As we've already mentioned in the last lecture, the entropy's a property. So the internally reversible process that we use to get to the value of entropy, it's just so that we can calculate an entropy property, but when you go from state 1 to state 2, it doesn't matter what path you use to get there. So entropy is a property, meaning we can use it even for irreversible processes. That's a tough one to understand, but it has to do with the internally reversible process part. Really just comes from how you go from your reference value to your value for the to your state value for the entropy. Again, it's a tough one to understand, but all you need to really know here is that entropy is a property, so it doesn't matter what kind of path we take. So the TDS equations that we derived hold for reversible and irreversible process paths. So it doesn't matter what kind of path we have going from state 1 to state 2, we can use the TDS equations. The second note just is talking about during a change of phase. Just remember that when you're under the vapor dome, the pressure and temperature of a substance remains constant. Just kind of a quick picture here to the left. So here, if we have a PV diagram with our vapor dome, and then we draw in an isotherm. So this is T is a constant. Recall that in this region that I'm going to highlight right there, the pressure and temperature remain constant under the vapor dome. So dP is 0, T is a constant. So then if you go back up to the yellow highlighted TDS equation, again, T is a constant, dP is 0. You can do some rearranging, and then you see that ds is equal to dH all over T. You can integrate that because T is a constant. And so the change in entropy during a phase change is equal to the change in enthalpy divided by the temperature. So again, just a convenient way to find the change in entropy. And remember that the temperatures that we use here are absolute temperatures. So just make sure you're always using an absolute temperature there, Kelvin or degrees Rankine. Okay, so one of the big things that we want to do with these TDS equations is to write property relations for an incompressible substance or an ideal gas. So that brings us to the third note. For an incompressible substance, okay, so what we're going to do is take those TDS equations and use them for an incompressible substance. So recall that for an incompressible substance, the specific volume remains constant, so there is no change in specific volume. And remember that the change in specific internal energy is equal to a specific heat times a change in temperature, and then that specific heat in general is a function of temperature. That's why we have C as a function of temperature. And so if you substitute those in to the first TDS equation, you'll end up with this relation. So the PDV term goes to 0. And then I just substituted in for the change in internal energy. And that can be rearranged to this form, and then we can integrate both sides. The left side will be just delta S, and then the right-hand side is the integral of the specific heat, which again is in general a function of temperature, over the absolute temperature times dt. So that is our way to relate specific entropy to temperature for an incompressible substance. It's solely a function of temperature. So that's kind of good to know, is that S is just a function of temperature for an incompressible substance. Okay. And if you're dealing with a substance where the specific heat does not change too much with temperature, so this would be like over small changes in temperature. So if you can say that you're dealing with a constant specific heat, then the right-hand side just becomes that specific heat, which can be pulled outside the integral, times the integral dt over t, which is just a natural log. And so we get this boxed-in equation for an incompressible substance. You can see it's pretty easy to work with. So it just makes it, again, more convenient than going back and forth to tables. You can quickly calculate changes in entropy directly from this equation for an incompressible substance. It's very important that you keep in mind the assumptions that were used in deriving this equation, namely this one in the box here, equation 286. It's for an incompressible substance, and this one in particular has a constant specific heat. If it's not a constant specific heat, then you have to go back up to equation 285 and actually work out the integral. Okay, let's do the same thing now, but for an ideal gas. So for an ideal gas, remember we have the ideal gas law. So that's the one thing I just underlined there. if you take, since we're dealing with a lot of differentials, if you take the derivative of the whole ideal gas law, so if you take the derivative of the left-hand side, let me just write this down on this side. So the derivative of PV is equal to the derivative of RT. The derivative of PV just is VdP plus PdV. And then the derivative of RT, R is just a constant, so it just becomes RdT. Then we have also in the ideal gas model that the change in specific internal energy is equal to CV times dt. And again, CV, it's the specific heat at constant volume, is a function of temperature in general. And then you have a similar thing for specific enthalpy. dH is equal to Cp dt. Again, those three things are what you get from the ideal gas model. So we can again substitute those back into the Tds equation, just right back up here at the top. For example, this one that I'm highlighting right now. So we can go ahead and substitute into there, and then do some rearranging. And I'm not going to go through all the algebra of that. You can sort of look at it on your own. But when all is said and done, when you go through all that rearranging, you end up with equation 289 right here. That the change in entropy for an ideal gas is the integral of Cp dt over t. So you get this first integral minus r natural log change in pressure. So that holds for an ideal gas. Okay, and you could also have gone through the algebra just a different way if you use the second Tds equation and derived a slightly different form of this equation. So this is going through the derivation starting at equation 290 and 291. If you just do it a different way, you could also rewrite it as this boxed in equation, equation 292. So here it's instead of, so if you look at the, let me see if I can scroll. So the one up at equation 289 was in terms of temperature and pressure. The one down here at 292 is in terms of temperature and specific volume. Just a different way to write it. And there, instead of dealing with Cp, here it's in terms of Cv. And instead of the natural log of P2 over P1, it's the natural log of V2 over V1. And or if you don't like specific volume and you prefer density, you could just rewrite it over here. Remember that specific volume is just 1 over the density. So that's how we got the second equation. So it's just you can find the change in entropy for an ideal gas a couple of different ways depending on which properties you're using. Okay, so again, in general, the specific heats are functions of temperature, so you would have to actually perform those integrals, which is tedious. We don't want to do that by hand, certainly. It can be done numerically, but there's a more convenient way to do it. We can actually pre-calculate those integrals for different temperatures, which is what we're going to do in the next step. But again, the boxed-in equations here, the point of them is to relate the entropy to other properties. Okay, that's all we're doing here is relating entropy to other properties, specifically here for an ideal gas. So again, if you look up at equation 289 and you look at this integral Cp dt over t, that's where Cp is a variable. It's a function of temperature. That's an integral you don't want to typically do by hand. But like I said, we can pre-calculate that. There are expressions for the specific heat as a function of temperature for different ideal gases. That relationship between Cp and temperature is just found experimentally, and people put a curve fit to that and then do the integrals. And so we can pre-calculate that. So that's what's being done here in equation 293. That integral is being performed between some reference value, call it T prime. T prime is just some arbitrary reference temperature. The reference temperature doesn't really matter, and the reason for that is because we're always dealing with changes in the specific entropy. It's always delta S. It's never S by itself. And since it's always a delta S, the choice of reference temperature doesn't matter. In fact, that's just kind of shown right down here. By the way, that integral from the reference temperature to some final temperature of Cp over T, we give that a special symbol, and we call it S naught. Okay, so S naught is just a an entropy-like quantity. It's just part of our relationship between changes in entropy and other properties. And just to show you that the reference temperature doesn't matter, that's what equation 294 is for. If you calculate S naught at temperature T2 and S naught at temperature T1, and you write it out, so at temperature T2 it goes from T prime to T2, and when you write it out for temperature T1 it goes from T prime to T1. The T prime values don't matter, they actually cancel one another out, and then it just goes from T1 to T2. So written in terms of these S naught values, and again, we can pre-calculate those S naught values and put them in a table, but if we write it in terms of S naught values, then we arrive at equation 295. So the change in specific entropy is equal to the change in S naught values, and notice that these S naught values are only a function of temperature. So that makes it a little more convenient when we prepare a table. And then minus the gas constant times natural log of P2 over P1. Remember, this gas constant, this is not the universal gas constant. It is not the universal gas constant. It's the gas constant for the substance you're dealing with. So it's the universal gas constant divided by the molecular weight. So I said that these S naught values can be pre-tabulated, and so this is an example from your textbook. These are the this is an ideal gas property table for air. These are not from this particular table doesn't come from the Excel tables, but this one's from the back of your book. You can see here temperature, specific enthalpy, specific internal energy, and now we have this other entry S naught, and that's the Cp over T dt integral. Okay. And just to kind of show you from our Excel tables, let me go back and find our ideal gas table for air, just to kind of show you. Here we are. I've got a bunch of stuff written on here. Let me erase it all. So our, again, ideal gas table for air, here's our temperature, specific enthalpy, specific internal energy, and now you see the S naught value. And you can see that the units for S naught are kilojoules per kilogram Kelvin. We also have these other quantities, P sub r and V sub r. These don't have any units to them. These are dimensionless. And we're going to talk about those in a moment. Those are for specific cases that we'll talk about toward the end of this lecture. Okay, so let's go back to our set of notes again. If we're dealing with a perfect gas, and this is where the CV and Cp values are constant, we can go back up to these equations. Let me just go all the way back up. Let's just stop here at equation 292. If it's a perfect gas, then this integral that I'm circling here, kind of highlighting in yellow, that can be rewritten if Cv is a constant. Then that integral can be rewritten with Cv pulled outside, and you're left with dt over t, which is just a natural log T2 over T1. Hold on, I just accidentally bumped something here. So that would be integral T2 over T1. Right, so if Cv is a constant, we can simplify it even further. And that's where we get equations 296 and 297. So instead of having that integral of Cp dt over t, now we just have Cp natural log T2 over T1. Or if we do it in terms of temperature and specific volume, then Cv times natural log T2 over T1. So again, these are very simple kind of equations to work with rather than always having to refer back to a table. But the boxed in equations are specifically for perfect gases. Ideal gases that have constant specific heats. Okay, now we're going to do some additional special cases. Okay, so now we've already talked about the general TDS equations. There are two of them. Then what we did is we applied them to an incompressible substance. Saw how to relate entropy to temperature in that particular case. Then we took the TDS equations and wrote them for an ideal gas in a couple of different forms. Showed how we can find some values in a table for the S naught value as part of our equation. And then just now I showed you what the equations look like for a perfect gas. Now we're going to take a look at isentropic processes involving an ideal gas. So isentropic just means that the change in entropy is 0. There is no change in entropy. Entropy is a constant. And so if we're dealing with an isentropic process involving an ideal gas, not a perfect gas, but an ideal gas, then the left-hand side of our equation, let me just go back up to kind of show you it. So it's back up here, equation 295 right here in the box. If we make the left-hand side 0, then what we get is equation 298 here. And then we can rearrange that a little bit and solve for the ratio of pressures. So we're just going to rearrange that equation. So we get P2 over P1, and then that'll be equal to the exponential of S naught T2 minus S naught T1 over the gas constant, which can be rearranged further. And what you see is that we get an expression involving exponential of S naught over R at the different temperatures. But we already know that we can find these, those quantities for S naught have been pre-tabulated, and we could certainly pre-tabulate S naught divided by R. That's easy as well. We could just take the S naught column, divide everything by R for a particular gas, and we can put that in a table as well. And that's what that PR value is in the table. PR is just defined as being the exponential of S naught over R, and it's solely a function of temperature. And so we can put that in our table. So that's what, let me go back up to this table here. That's what this PR value is it is, the PR is just this exponential S naught T over R, and then we can use that by relating it back to the P2 over P1. Okay, so let me just kind of show you so that we can use our definition along with equation 299. And then we see P2 over P1 is equal to PR at T2 over PR at T1. And so this particular equation, this is for an ideal gas and an isentropic process. Those are the key assumptions that we have to have in order to use those PR values. So again, it's just a more convenient way to be able to find changes in pressure just very quickly from the table. You use the PR values. And again, the PR values are pre-tabulated. You see them here in this table, same sort of thing in our Excel tables. And it's highlighted here in particular just to show that delta S is 0. This means that it's isentropic. Okay, so we can use that ratio of PRs for isentropic ideal gas processes. And you can do the same sort of thing for the specific volumes rather than, so we can use, for example, let's see, where is it? Yeah, here we are. So we could use, for example, this equation up here. Sorry, it's so messy, but equation 292, and again, make the left-hand side equal to 0 if it's isentropic, and then do some rearranging of all that. And if you do all that, you'll get the ratio of V2 over V1. Here, actually, what I did is I made use of the ideal gas law. Actually, it's easier to make use of the ideal gas law. So here I used the ideal gas law, put the ratio of P2 over P1 in terms of PRs. And so then we define a new quantity, VR, which is just RT over PR. And then you'll get the specific volume ratio related to the VR values. And again, this is if you're dealing with an ideal gas, isentropic process. Those are the key assumptions to get to that equation. So it just gives us a convenient way to find the ratio of specific volumes for isentropic processes involving ideal gases. And again, those are pre-calculated and put back up into the table, and that's what the VRs are. Okay? So again, you can only use those VR values when you're dealing with ideal gases and isentropic processes. Isentropic processes, I should just point out, these are processes when we, again, they're kind of related to our ideal case when you don't have a bunch of irreversibilities. Okay, so you'll see that a little bit later in the course. So isentropic processes are ones that we often like to look at as being kind of the best case scenarios. All right, one last thing. I know that we're going through a lot of equations here. By the way, I should just point out you don't need to know these derivations. The derivations are all in these notes should you ever need them for some reason. The thing that I really want to highlight to you by going through this is just to show you where the equations come from, and most importantly, to make sure you understand the assumptions that go into the equations, because it's the assumptions that you really need to know to use the equations properly. So the last thing that we'll do is we're going to go back to our perfect gas equations. Let me go back up here. These equations 296 and 297. And if we are dealing with perfect gases undergoing isentropic processes, so again, if it's isentropic, the left-hand side, the delta S will be 0. So if it's a perfect gas and isentropic, we can start getting some convenient relationships between variables. So that's what this is down here. Equations 304 through 306. They're just taking those perfect gas equations. The left-hand side is 0 because we're saying delta S is 0. And then doing a little bit of algebra on this. And we end up with the boxed equations on the right-hand side. So these relations, these are used all the time in the analysis of ideal gases or perfect gases. These just give us really convenient ways to relate changes in pressure, temperature, and specific volume or density, as I've shown at the bottom box. So we'll use those a lot. And in fluid mechanics, gas dynamics, they're used all the time because we often make the perfect gas assumption. So the assumptions that go into this equation are that you're dealing with a perfect gas and isentropic. Namely the isentropic process. I should point out that when we say something is isentropic, it refers to a process. A state cannot be isentropic. A process can be isentropic because you have to have a change in the entropy. It has to be two different entropies that are the same value. That's what makes it isentropic. Okay. The other thing that I show in the box here, equation 307, is that you can combine some of those perfect gas relations, and you can show that you can write it as a polytropic process. So if you're dealing with an isentropic process of a perfect gas, it's a polytropic process where the constant, remember a polytropic process is one that looks like this. This constant is equal to the specific heat ratio of the gas. K is our specific heat ratio. Just remember K is our Cp over Cv. And for air, it's 1.4 over a wide range of temperatures. So anyway, that's why we often look at polytropic processes, is because this kind of equation holds true for ideal gases under various conditions. So for example, if you're dealing with an ideal gas that is undergoing an isothermal process, then the N is equal to 1. If N is equal to 0, then that makes it isobaric. Basically, the pressure is a constant. If the constant is equal to plus or minus infinity, that actually is a constant volume process. And when N is equal to the specific heat ratio, that's a isentropic process. Okay. Let me say one last thing. This is actually kind of an interesting real life note here. This equation 8, or this note number 8. I talk about situations where the isentropic assumption is a reasonable approximation to real life. One that we often encounter when we deal with high-speed flows of gas is flow through nozzles and diffusers and such. So let me just draw a nozzle here. And this is something you'll learn in fluid mechanics, but when you have a flow of a gas or any sort of fluid through a nozzle like that, what ends up happening is near the walls of the nozzle, you get what's called a boundary layer. The boundary layer, it's just a very thin layer next to the walls where all of your viscous effects occur. So viscosity is like the internal friction of a fluid. And most of that what we call viscous dissipation, kind of the frictional dissipation, if you will occur in a very thin layer next to the walls. And this is called a boundary layer. This is something you'll learn about in fluid mechanics. All of the stuff in the middle, there's very little viscous dissipation, very little internal friction occurring there, turns out. So the flow actually in the middle can be considered internally reversible. There's just no irreversibility in that part. In the red zone near the walls, there's a lot of irreversibility because of the internal friction. But in the yellow region in the middle, it's internally reversible. In addition, often these nozzles are not that big, and the surface areas are not that big, and so the amount of heat transfer going through the walls is typically very small. So the heat transfer into is about zero. It's just small. It's negligible. So what you end up having is a reversible and adiabatic kind of flow through these nozzles. Okay, so reversible and adiabatic. And if you go back to remember the entropy equation, it looks like this. Well, if it's reversible, that means the sigma is zero, so that's reversible, internally reversible. And if it's adiabatic, delta Q is zero. So that was zero because it's adiabatic. And if that's true, then what you end up getting is delta S is zero. So that means it becomes isentropic. So when you're dealing with high-speed gas flows through nozzles, for example, those flows are often assumed as being isentropic because most of the flow field is reversible, and they're often assumed to be adiabatic, very reasonable engineering assumption, so then they're isentropic. So then you end up having high-speed flows of gases those processes are considered isentropic, and if the temperature range isn't too large, then you end up being able to use these boxed-in equations because those equations are for a perfect gas for isentropic processes. So that's kind of a place where you would use these equations in practice, is by modeling these kind of high-speed gas flows. So it's actually quite useful for us. By the way, since I have the entropy equation here, I should just point out that isentropic does not necessarily mean that a flow is reversible and adiabatic. So it doesn't work in reverse here. And the reason for that is it's possible I could just have, let's say, a heat transfer out of my system. I could make this negative, so because delta Q could be negative, right? I could have heat transfer out of the system and a process that is irreversible in such a way that I could sum those together to make it equal to zero. And so it is possible, which would mean it's isentropic. So I could have an isentropic process where delta S is equal to zero, but it's not reversible and it's not adiabatic. You can see here this is irreversible in this particular case, and this is not adiabatic. Right? So I can still have an isentropic process that's not reversible and not adiabatic. But if it is reversible and adiabatic, then it must be isentropic. Okay, so this is a typical kind of short answer question you might get on an exam. Are all isentropic processes reversible and adiabatic? And the answer is no. It's very special. You'd have to have a very special case where the heat transfer and the irreversibility just perfectly match one another. So it's extremely unusual, but it's not impossible. Okay, I think I'm going to go ahead and stop the kind of background Actually, I'm not going to do that. I'm going to go back up just to summarize because we covered a lot of equations. I'm going to go back up to my notes, and somewhere in here, just give me a moment. I wanted to show a summary of our, here we are. So I just want to kind of quickly review what we've talked about here. Okay, so this is at the kind of the lecture style set of notes here. So for an incompressible substance, I'm just kind of summarizing everything that we've had to say for an well, first of all, actually, let me go even further back. Tds equations, there are two of them. We derive them here. They just relate the specific entropy to other properties. These are true for any substance. The only thing is that the substance has to be simple and compressible. Just basically means that you ignore kinetic energy, potential energy, and only consider PDV work. Okay, so those expressions in the boxes there are true for whatever substance. And then what we did is we used those equations for an incompressible substance. So this kind of red highlighted region here summarizes everything we have for our incompressible substance model. So liquids and solids are often considered incompressible. If it's incompressible, the specific volume is a constant. The specific heat, there's only one of them, C. It's generally a function of temperature. The internal energy is a function of temperature. The specific enthalpy is a function of temperature and pressure. And we just derived just a little bit ago that the specific entropy is a function of temperature. The change in specific internal energy is the integral of C dt. That's this bullet. The change in specific entropy is just the change in specific internal energy and PDV. Change in pressure times specific volume. This comes from just our definition of the specific enthalpy. And if we end up just taking the derivative of both sides and then integrating, it'll end up looking like this, right? Because the P delta V term is 0. And then what we just did in this lecture is found the expression relating the change in the specific entropy to the integral of the specific heat. And then if the temperature range isn't too large, where we can assume that the specific heat is about a constant, then things get much simpler given in the following three equations there. Okay, so that summarizes everything we have for an incompressible substance model. It's just convenient to keep those things in mind. Then what we did is we looked at an ideal gas, and let me just go to the summary of that one. So here we are. There's more to the ideal gas model. It's a little more complex. So for an ideal gas, we've got the ideal gas law. We also have our expressions for the change in the specific internal energy and change in specific enthalpy. So there we make use of two different specific heats. And again, this is something that was covered in the first exam, but I should mention it here, is you can still calculate the change in internal energy even if a process is not at constant volume. Same sort of thing with specific enthalpy. You can still calculate the change in specific enthalpy if the process is not at constant pressure. The CV and and the reason for that is because specific internal energy and specific enthalpy are properties. You can find them at any state. The path between state 1 and state 2 does not matter. The constant volume and constant pressure definitions come into finding the value for the individual U and H. It's like going from the reference value to state 1. And that's how the CV and CP, that's where the constant volume and constant pressure come into play. Anyway, and then what we did in this lecture is we found how to find the change in specific entropy between two different states. So this was our kind of derivation. We introduced this new property called the S0 value. And the S0 values, we can find those from the ideal gas tables. And then we said if we were dealing with an isentropic process, then we can use the PR and VR ratios also in the ideal gas tables. So you can see here that to get to that, you have to first have an ideal gas, and then the process has to be isentropic. Okay. And then if you're dealing with perfect gas, where the CV and CP are constants, two different constants, then everything gets much simpler, and you're left with these expressions here where you have delta U is just CV delta T. You have our expressions that we derived in this lecture for changes in specific entropy. And then again, if you're dealing with an ideal gas and the process is isentropic, then you get these very convenient relations that we can use. And again, just the K here is the specific heat ratio, CP over CV, which is equal to about 1.4 for air. So that's a quick summary. These little bits here for the incompressible and ideal gas summaries are pretty convenient. Just make sure you're familiar with those. All right, I'm going to go ahead and stop the lecture here, but what I'll do is work through a couple of problems in a couple of separate videos.